Greetings everyone, this is Mr. Mullen. This is a quick podcast to get you started on this worksheet. And so there's a lot of new ideas here, so I just want to kind of do one of each type for you, and then that will give you enough to kind of go through and figure out how to do this. So the first part, this is talking about all strong acids and bases. And so when strong acids and bases are put into water, they're going to dissociate completely. That means 100% are going to break into ions. And so depending on if it's a strong acid or a base, it's either going to break into all H plus or H3O plus is what ends up happening when it actually finds a water molecule, but all H plus or all of those bases are going to shoot out and kick out an OH minus, and we're going to have a bunch of OH minus floating around. And so 100% is going to break apart. So let's look at number one. And notice that for water, whenever I look at water's equilibrium, this is called Kw, when I multiply these two concentrations together, regardless of how big one is or how small the other one is, they always end up equaling when multiplied the same constant value. And this is just the equilibrium constant for water. So when I look at this first one here, what is the concentration of hydronium ions? So we're looking for H3O plus. You can also think of that like an H plus, when the concentration of hydroxide ions is this. So for this problem here, it's telling us directly what my concentration of OH minus is. Okay, it's giving that to me in the problem. So what I can do is I can know that Kw is always equal to the concentration of hydroxide ions times OH minus. Okay, that's just what I have up here. And so if I wanted to find this, we just divide both sides by OH. And what that does for us now is it gives us a new expression. H3O plus is equal to that Kw value divided by my hydroxide ion concentration. So now we can just plug stuff in. Kw for water at 25 degrees Celsius, which we're going to assume that this is always going to be 1.0 times 10 to the negative 14th. And so if I divide that by my OH, which was 3.0 times 10 to the negative 5th, we're going to be able to calculate our unknown, our H3O plus. And so when I plug all that stuff in, I'm going to get 3.3 times 10 to the negative 10th. And that's going to be moles per liter of H3O plus. Will be our final answer. Now notice I've done this, I have this little thing here. If you want to go from H plus to OH minus, and this is available on Haiku, notice I have the different equations to go back and forth. The one we just derived is right here. And then if you want to go back the other way, you could just use the other version of that one. So that would be a helpful table. And so looking at the next step here, number 3, I have a strong acid. Now all strong acids are going to break apart completely. You'll notice in this acid there's an H there. And so all strong acids, when dumped into water, okay, when they're dissolved into water, are going to break apart into 100% H plus and whatever that X minus thing is. So if this was 1 mole, this would be 1 mole per liter, this would be 1 mole per liter, because all of it breaks apart. So since this is a strong acid, they give me my concentration of this, I can therefore say, well, it's going to be the exact same. And so I'm going to go ahead and say, now that I know my H3O plus concentration, and I want you to recall that water has, on normal, neutral water, has 1 times 10 to the negative 7th concentration of H plus just normally. Now if I add 0.01 moles per liter of H plus or H3O plus, this number here is so dwarfed and so insignificant that we ignore that and we say all the H plus really is going to be coming from just my acid. That other number is so small. So this is our concentration for H plus. So using that expression, based upon this idea here that we just looked at, now we're going to solve for OH minus. So I'm going to divide both sides by H3O plus. And my new expression is going to be that my OH is equal to Kw divided by H3O plus. And then you can go through and you know what Kw is. You know my concentration of my acid now is just whatever I dumped in there. And you can get our final answer. times 10 to the negative 112 moles per liter. And this is of OH minus now. We're finding the opposite. So you're going to repeat those steps. Number 7 is very similar, except now we're talking about strong bases. And so in a strong base, all of this is going to break apart into ions. So what I'm going to do is I'm going to say, well, if NaOH breaks apart in water, I'm going to have Na plus and OH minus. If it's a strong base, that means that all of this, okay, is going to break apart into all Na and all OH minus, 100% will. And so that means if this was 10, this would be 10, this would be 10. But it's not 10. In this case, it's 2.3 times 10 to the negative 4th moles per liter. So using that idea and using the kW for water, we're going to go back and we're going to figure out what is my H plus. What is my H3O plus? Question mark. And so using that expression, we can rearrange it a little bit. And we're going to get that H3O plus is equal to Kw divided by my OH minus. And that's just rearranging that equilibrium to solve just for H3O plus. So when I do that, 1.0 times 10 to the negative 14th, divide that by my 2.3, and oops, and then we're going to get our final answer. We're just going to punch it in our calculator. We're going to get 4.3 times 10 to the negative 11th moles per liter, and that's H3O plus. So you're going to repeat those steps. Number 10, you're going to try to figure out which one is more acidic. And so acids are going to have greater concentrations of H3O than OH minus, or you can compare the pHs. So if the pH is less than 7, it's acidic, or it's more acidic. Okay, there's two ways you can do that. Compare the two concentrations so you can figure out how to do that one. I want to help you here with the last page. So this one here, you're going to actually be calculating the pH. And so you're given in this first part of the problem the hydrogen ion, or H plus. Now, these are going to be interchangeable. H plus or H3O minus, those are going to be interchangeable. They mean the same thing. So I'll do the first one for you, put this number in scientific notation. So remember, we moved back the decimal behind the first number. So this was 1 times 10 to the, I moved it back, negative 1. And so when I go into my pH now, we're going to be going from H3O plus to find the pH. So there it is on the top. To find pH, it's negative log of H3O plus. So I'm just going to take the negative log of this number here, 1 times 10 to the negative 1, and we're going to get an answer of 1. But you're going to actually need a 0.0 here, and let me explain why. This little 10 to the negative 1, for log base 10, that power of 10 is always this first term. Okay, that represents that first term. And so because that's a placeholder, it's not a sig fig, this number here actually becomes the first sig fig for pH. That's going to be the first sig fig for pH. And so I can do the next one. There's one sig fig here, so I'm going to move my decimal back 2 places, 1 times 10 to the negative 2. So now I have 2, and then I need my 1 sig fig, because there's 1 sig fig over here, and that's going to be here, 2.0. And so when I punch that in my calculator, you're going to get that number, 2.0, and you can go through and figure that out. When you get to the bottom half, you're going to be kind of going in between these different things, going back and forth. Now you're going to go in reverse. To find the H3O plus, you're going to take 10 and raise it to the negative pH. Okay, to find the OH minus, you're going to take 10 and raise it to the negative POH. And you're going to go through and figure out what these different values are. And so if I took 10 raised to the negative 3, you don't have to show this work, but 10 raised to the negative 3.2, you're going to get your answer here in concentration. So this is 1 sig fig, so I'm going to put 6 times 10 to the negative 4th. Okay, to find the POH, there's a couple different things that I can do here. I can go and use that table, and I can go from pH to pOH. And so that's one thing I can do. They both add up to 14, so 14 minus 3.2 is 10.8. And then from there I can go to OH minus. There's a couple of different ways you can do this. I can either take the pOH and raise it to 10 raised to the negative 10.08. I could do this, and you're going to get 2 times 10 to the negative 11th. Or you could do what we did in the last problem, the last part of the worksheet, and you could, since you know H3O plus and you know KW, you could find OH minus that way. So there's a couple of different ways to do this. And so what I want you to do is I want you to go through and try to figure out how you're going to go between these. And I hope that this was helpful.